Hi, welcome or welcome back. In today's video, we're going to talk about one of my favorite subjects in calculus, which is derivatives. So last time we talked about an application of limits, which was continuity. So this is another application of limits, if you will, to start off, because I can define a derivative using a limit. So let's start with our limit definitions of a derivative here. So first off, I have this one right here. This is probably the most common one that we'll see. And this is showing that I can find the derivative of a function at any value x if I calculate this limit. This is the limit is h goes to 0 of f of x plus h minus f of x divided by h. And we'll look at a few examples of this in the next video. Additionally, I can also find the derivative of a function at a specific point. So if I'm given a number a, I can find the derivative at that exact value. So you'll notice these two are the same, but instead of x, I have an a, and then this is just another definition of a limit at a value. We can think of a derivative as the slope of a tangent line. In case we need a little refresher of what a tangent line is, I have a graph here from Desmos, shout out Desmos, that shows this function here. So this is my function, and then a line that is tangent to it. So a tangent line just touches in one point, and this happens to be that point there. The slope of this tangent line here would be the derivative of this function at this point. And I can actually use this tangent line as an approximation. So if you've heard of linear approximations, that's what we're doing. If you notice, when this tangent line is really close to the function, it's a decent approximation for the value of the function. Another way that I can think of a derivative, in addition to it being the slope of the tangent line, is also the instantaneous rate of change, or sometimes we'll just call it the rate of change. So the derivative is the instantaneous rate of change. Here are just a few notations that I can use when describing a derivative. Big deal alert. So this theorem right here is very important, very valuable. It says if f is differentiable at a, then f is continuous at a. So if I'm differentiable, I'm continuous. However, big but, the converse is false. Continuity does not imply differentiability. So if it's differentiable, automatically I can say if it's continuous. If it's continuous, it may or may not be differentiable. So we can head on over to Desmos once again for an example of this, and this is the function absolute value of x. So at this point right here, 0, 0, the absolute value of x comes to a sharp point. Sharp points and cusps are not differentiable. So although this function is continuous, at 0, 0, it is not differentiable. We can also show that it's not differentiable by computing the limit from the left and the limit from the right, and we'll see that those are not equal at 0. So while the limit definition is very useful, it is very arduous. We do this really fun, cool thing in math where we make you learn the hard way of doing things first, because if you knew the easy way, you would definitely not do the hard way. This is kind of an example of that. This is the hard way. This is the scenic route, but we do have a few shortcuts. So here's a list of common derivatives. These are things that I can memorize, right? And this is a shortcut to finding a derivative. So instead of taking that whole limit, doing all that algebra, I can just go ahead and use these right here. So you can screenshot this. I will also have all the notes linked in the description box as a PDF, as always. So first we have some trig derivatives right here. And again, highly, highly, highly recommend memorizing those. I got some inverse trig derivatives right here. Exponential and logarithmic derivatives. This one right here happens to be my favorite. Derivative of e to the x is e to the x. That's my favorite derivative. We got polynomials. This one comes up sometimes, right? So derivative of a constant is 0. The rate of change of a constant, that slope of that tangent line would just be 0 because it's a horizontal line. Derivative of a constant times x is just the constants. 3x, for example, derivative there would just be 3. And again, we'll go through a few examples in the next video. Here are some rules. So these are very important to memorize. Like we had the limit laws, this is kind of a similar thing for derivatives. Unfortunately, these are maybe not quite as straightforward as the limit laws. So I have a constant multiple rule, which we kind of saw here. which means if I have a function times a constant, I can pull the constant out in front. That is similar to the limit laws, right? I can just throw the constant out in front, find this derivative, multiply the two together. Sum and difference is the same as the limit laws as well, right? I can just do them individually. So if I'm adding or subtracting two functions, I can find the derivative of each of them individually and add or subtract those derivatives together. Now here's where we deviate from the limit laws. So product rule, I can't just break them apart and then multiply the answers together. I actually have this really interesting formula for product rule. The way I like to memorize product rule is the first one times the derivative of the second plus the second times the derivative of the first. So that's product rule right there. Great one to memorize. Because both multiplication and addition are commutative, this order right here really doesn't matter. So you can flip-flop these if you'd like, as long as each term has one of the functions unchanged multiplied by the other function's derivative, and then the other term has the opposite there. So as long as each term has a function and a derivative, and we got everything covered, it doesn't matter what order you do it in. I tend to do it in the same order every time because that's how I have it memorized. Next, we have the quotient rule. So the quotient rule, again, different from the limit laws, is a little more work. So if I have a function on top and a function on the bottom, then this ends up being their derivative. The way I have this memorized is bottom for the bottom function, d top, derivative of the top, minus top for the top function there, d bottom, derivative of the bottom, all over the bottom squared. Some students like to memorize this as low d high minus high d low. However you want to get this down, no big deal, right? Whatever works for you, that's what you should do. Then I also have the power rule here. So if I have a power up here where n is a number, right, like x cubed, I first drop down the power and then I subtract 1 from it. So drop down the power, subtract 1 from it. And again, we'll look at some examples in the next video as well. Chain rule is the last one here. This is for composite functions. I think I'm going to do an entire video just on chain rule because that one is really important. It comes up a lot and it's something that students often struggle with. But for now, it'll be here along with all the rest of them, and this will be available to you. So please stay tuned for the next video where we'll go through some examples of how to calculate a derivative, both using the limit definition and using some of these properties here. So I'll see you in that one. Thanks so much. Bye.